Hello everyone, my name is Pulak Sarangi and I'm a PhD student in the Smart Sensing and Information Processing Lab headed by Professor Piyapal. So our lab primarily focuses on the mathematical and algorithmic foundations of signal processing and data science. So I would try to briefly cover the main research themes that our group is currently focusing on. The first topic is about spatiotemporal computational sensing with sparse arrays. So in this topic, our focus is on understanding how do we place our sensors to measure a given signal. In a variety of estimation problems, if we move away from the conventional way of uniformly placing our sensors, if we adopt a sparse strategy to place our sensors, then we can often achieve more with the same sensor budget. Once we have sensed our signal using this unconventional sensing geometry, now we have to computationally recover our signal of interest. And this is what gives rise to inverse problems. So this idea of designing sensor geometries is extremely relevant in the context of target localization using radar or sonar, and even in the context of millimeter wave communications, where we have to decide how do we place our antennas that is eventually going to shape the effective channel. Now moving on to solving these high-dimensional inverse problems. So as mentioned earlier, often we are interested in recovering a high-dimensional signal, but we only observe a distorted version of the signal through some measurement map. And often the number of measurements that we have are limited. So our goal is to reconstruct this original signal from these limited measurements. And often these problems are ill-posed, and we have to exploit suitable types of priors to be able to perform this reconstruction. So one of the main goals is to understand how many measurements do we require to perform this reconstruction. And the second question is how to design computationally efficient algorithms that can enforce these priors on our desired signal. The third topic is about correlation-aware sparse signal processing. So we have shown that by exploiting the additional correlation structure present in the data, in addition to sparsity, we can operate in compression regimes which is much higher than simply relying on sparsity-based techniques. And finally, we also work on understanding the fundamental limits of super resolution. So in super resolution, there is an interplay between what kind of sensing geometry that we use and what are the type of priors that we use. So we show that fundamentally it is possible to achieve much better performance by using certain types of priors such as non-negativity, correlation, or binary priors, which are extremely relevant for super resolution. In addition to these theoretical problems, we also actively collaborate with people in neuroscience and radiology. So in one of our projects, we apply the idea of computational compressive sensing for cellular MRI to develop new sampling strategies. In our collaborative project with the neuroscience department, we developed new super resolution algorithm to decode the spiking activity of neurons from calcium imaging data. Thank you.
For more information, please visit ece.ucsd.edu.
Okay, thank you for playing the video. So I guess people got to know about my works in an abstract, like kind of snapshot way. If you want to know more about myself, I have maybe a couple of slides, and then I can take questions, okay? So I can share, right, my screen? Can I? Okay. All right, let me see. Host disabled attendee screen sharing.
Does that work?
Who's the host here?
It might be me.
Okay. So you have to enable me to share my screen.
Did it work?
Let's see. Yeah, good.
Okay.
You made me co-host, didn't you?
I think so, yeah.
That's the easiest. Okay, good. So, okay. So can you see my slides? So I'm an associate professor of electrical engineering at UCSD. I'm originally from India, where I did my bachelor's in IIT Kharagpur in electronics and electrical communication engineering. After that, I went to Caltech, where I did my master's and PhD in electrical engineering. My advisor was Professor P.P. Vaidyanathan. Okay. So I am all through and through electrical engineering background. That's what I want to tell you. If you want to know about my research profile in a nutshell, what kind of problems interest me, what is my taste in research, there are two things to give you a very broad overview. I'm primarily interested in mathematical and algorithmic aspects of signal processing. Okay, so and many of these mathematical and algorithmic aspects are super relevant for today's high-dimensional data science. Okay, so the similar ideas and approaches are borrowed from signal processing in the high-dimensional regime, but again in the high-dimensional regime, non-trivial modifications have to be done to account for the fact that what you develop in a classical regime where number of samples and number of parameters do not grow commensurately, okay? When you try to apply those techniques in the high dimensional setting, many unexpected things happen. So you have to move away from classical ways of thinking about problems and tackle the high dimensional curse of dimensionality, so as to speak, by developing fundamentally new ways of looking at this problem. So that is primarily what interests me. Applications are my excuse to develop new mathematical or theoretical aspects, okay? So I'm primarily a theoretician, and I also like collaborating with practitioners because I get to learn what kind of problems they're interested in and extract the core foundational fundamental mathematical idea from there. That's my take on research. So if you want to do research with me, this will be the general strategy, okay? So in terms of data collection or visualization and this and that, I rely on my collaborators. But if the data collection visualization there is something fundamental, mathematically fundamentally different way of doing it, then it interests me, and then I will kind of think more about it. But in terms of real data sets and all that, I am lucky to have collaborators who provide me with that so that I can focus on the theoretical aspect. If you ask me what kind of things I'm curious about hows and whys, how something works. And once you understand how something works, then you ask the deeper question, why it works, why not this, right? So I'm more biased towards the whys than the hows. So I'm not just happy with, okay, implementing something on a data set, getting some results, moving on to the next topic. If that particular technique shows surprising results in certain data sets, I would certainly want to understand why it happened. Will it happen in other cases as well? Is there something fundamental that connects apparently disparate applications? All right, so that's pretty much a nutshell. And I think Pulak already told you more about some of the research topics that are of interest to me, but I will just keep this slide on display. And I would love to know what questions you guys have about my work. I can probably show you, maybe I can show you my group photo. People like showing group photos. Let me see if I can. So if you want to know, this is from a recent talk I gave for first year graduate students, actually, just an overview kind of talk. Anyway, let me go to, I'm sorry. Just let me try to introduce what my group is right now. Maybe. Yeah, so this is my research group right now. So one of them is a visiting student, but the remaining are my PhD students who work with me. Two of them have graduated, so these are my alumni. Hang Chao, who is currently an assistant professor in University of Michigan, Shanghai Jiaotong Joint Institute, and Ali, who just graduated a few months ago, and he's a joint Qualcomm. And some of the highlights of our research group are also listed. Okay. So please feel free to ask me any question. Anybody?
Hi, I had a question. Can you talk a bit more about your work on the generative priors side?
Who is this? I'm sorry, I
Um,
cannot, from your voice alone, I cannot make out. Can you please introduce yourself?
Hi, I'm Chinmay. I am a
Okay.
second year master student at UCLA.
Okay. Hi.
Yeah, so I wanted to know a bit more about your work on the generative priors side.
Okay. So you see, generative priors. So basically in the high dimensional regime, right? If you want to solve a estimation problem or an inverse problem, what happens in the high dimensional regime is you have to estimate a lot of unknowns from a limited amount of data. Okay. So you can say, oh, but these days we have a lot of data. Depends on the application. Not all applications are based in computer vision where you have large image data sets to play around with. Okay. So actually many important applications, especially what we call the mission critical applications, concerning Department of Defense, for example, or applications in biology, where it is very difficult to get, large training setup, which is very representative of the realistic scenarios that you're going to face. So in that sense, you have to make do with whatever data you have, or even worse, you may have to work with synthetic data sets which have biases in them, okay? So whatever may be the reason, you have to learn something, okay? Learn something, learn some parameters, learn a signal of interest from a few measurements. Those measurements may be corrupted, whatever. So the object that you have to learn is living in a high dimensional space, okay? Very high dimensional space. But the training data is not scaling commensurately with the high dimensional size of the object. So I think I have one of the slides where I can talk about, but I can just mention this briefly here. So in that particular regime, classical statistical estimation techniques do not work well. You see, because classical estimation algorithms, their guarantees are pretty much derived in the regime where your number of unknown parameters is held constant and you have more and more data. In that regime, you talk about consistency, efficiency, etc., right? But in the regime where your number of data, amount of data, and the number of unknown parameters of the model are comparable with each other, those bounds that you developed in the asymptotic regime will no longer be adequate. If you use those bounds, you will not get realistic, meaningful results. So you have to move away from this classical estimation theory and you have to use something extra, okay? That about the object that you're trying to recover. And that extra knowledge is called prior, okay? So any optimization problem has two parts. One comes from the data, that's the loss. The other has the prior, typically, okay? The other has the prior, that has nothing to do with your data. That is your pre-concept or pre-information somebody gave you, okay? And this information can be captured in various ways. You can capture them in terms of the geometry of the data set. You can capture them in terms of statistical priors that you know, okay? Or a model that you think of that generated the measure, that generated the object of interest. So generative priors is that kind of a prior where you assume that the object that you're trying to recover follows a generative model. If you go back to classical signal processing, can you, because you guys, you already are a master student at UCLA, tell me of classical signal processing. Tell me what comes to your mind when you think of generative model, let's say for speech.
A hidden Markov model.
Or even go back to even basic DSP, an autoregressive filter, right? A linear prediction filter is a generative model.
Yeah.
Correct, right? So a generative model is basically something that generates a complex object from a lower dimensional space, okay? You can think of it in the parlance of neural networks or encoder, autoencoder terminology. We use the word latent code, okay? So decoder part of your autoencoder is typically considered, can be used as a generative model.
Yeah.
Okay, so you map, although the signal that you're observing or the image that you're trying to reconstruct, let's say denoising, deep blurring, whatever your application of interest, is high dimensional, it is ultimately generated by a low dimensional code through a complicated function, highly nonlinear function, parameterized by the neural network. Okay, so people have pre-trained networks these days available, right? They're very, very complex, lot of parameters. Why not use them as a prior? Right? It's not just about training networks. Training is one aspect of the machine learning problem, but the more interesting thing is, what do you do with a network that has been trained? How can you use it efficiently for an actual inference task. And one of the tasks is that of, let's say, a parameter estimation problem or an inverse problem more generally. Okay. So in this kind of inverse problems, instead of using a handcrafted prior, so image processing, computer vision is full of examples where people came up with these beautiful priors to regularize the problem in the setting where in the high dimensional regime. So instead of using handcrafted priors, you are actually using a prior that has been learned from data. How has it been learned? By training, let's say, an autoencoder or a variational autoencoder.
Yeah.
Okay. So that captures a prior. Now, can you use that prior to solve the inverse problem? If you can, suppose somebody gave you some guarantee. If you use this, if you use this generative part of the autoencoder as a prior, you will come within an error ball of the ground truth. Somebody's give you this prior, right? Now, using that guarantee, can you now tell me if I want to use this for a specific task? Okay, let's say for compressed sensing, what kind of guarantees will we get? So that is my work on compressive sensing with generative priors, or more generally inverse problems with generative priors. And these inverse problems need not be linear. Compressed sensing inverse problems are typically linear measurement models, but ill-posed.
Yeah.
It could be nonlinear as well. Yeah. And nonlinearity is not something to be taken lightly, because you can take it loosely and say, I'll just train something and test on data. But the nature of nonlinearity hugely controls your convergence properties, the way these things, functional mappings happen between the latent space and the image space and so forth. So for specific kinds of nonlinearities, you can get very specific kinds of these mappings. So I'm interested in those mathematical aspects of these generative models. Yeah.
Okay. Yeah, definitely. That sounds quite interesting. Thank you.
Excuse me, Professor. Right now in the agenda, a break from 4:10 to 4:20. So you would like to keep talking with the students. They have until 4:20, until the next event.
My God, this is like. How can anybody know anything, understand anything in this 10 minutes? Okay. I would love to talk to all of you. I know I'm meeting one-on-one with several of you, okay? I look forward to meeting you guys. And we can chat more about these things. I love chatting about this. You know, I can get carried away, but yeah. All right. Okay, so they have to move to the other meeting. Is that what you said?
Well, they have a break until 4:20.
4:20. Oh, okay. All right. Okay, then there's time, yeah. Any question, please?
Okay, so when you're talking about generative priors for images, you're referencing like the work Deep Image Prior, right? I was curious.
Deep Image Prior uses untrained networks. I'm talking about pre-trained networks.
Are you talking about pre-trained networks? Oh, well, regardless, I was just curious if you have any thoughts about like Deep Image Prior.
Oh yeah, I have a lot of thoughts.
Or like, do you guys have any interesting theoretical results? Any like interesting theoretical directions you're trying to go with?
So the most relevant work in Deep Image Prior, theoretical understanding of Deep Image Prior, is with respect to the training of this. Basically, these are untrained models. So they figure out the parameters of the untrained network given just one image, right? That's what I'm guessing you are a little bit familiar with Deep Image Prior.
Yeah.
Correct?
Yeah, one of my yeah.
Okay, I see. So one of the theoretical work that is being done is by Reinhard Haeckel from Munich, I believe. Have you followed his work?
Yeah,
so
I've heard of him.
He writes. He has most of the theoretical work that has been done. He basically talks about how gradient descent on these kind of problems tries to find smooth solutions. Okay, so it has a gradient descent has a bias. You see, ultimately, how you are finding a solution to this problem, right? So basically, what is Deep Image Prior? You randomly initialize the latent code, and then you learn the weights of the network, right? Using gradient descent. Nobody asked you to use gradient descent, but that's what people use usually, because the computational tools, everything, the packages that are available are optimized like crazy for gradient descent in particular. Now, if you use gradient descent, what kind of model will it find for you? Number one, right? Number one. Number two, how will that model generalize? So in the Deep Image Prior case, you're not really worried about generalization, because if you are given a new image, you will again train the model. Clear? It's not like you will use that model for the next image. So in this case, the question is slightly different. So in this case, the typical nature of theoretical work that happens is, I have a CNN. They typically use convolutional neural networks. And I do gradient descent to learn the parameters by randomly initializing the code. how close can I get